This video will look at some more bridging between GCSE and A-level, and what we're going to do is look at completing the square. When we have a quadratic in the form ax squared plus bx plus c, then we can complete the square. And in terms of the way we write this, we can write it as now p and then x minus q all squared plus r. I like to get away from this idea though. It's a little too formal for my liking. Now, the idea with a completed square is that we can take a lot of information from a completed square. We can also use it to solve. And the information that we can take are things like the axis of symmetry, the minimum point on the graph, and so on and so forth. So what we'll look is we'll look at the basic skill and what this does in terms of a graphical representation of the quadratic. Complete the square for each of the expressions below. Now the technique that I'm going to introduce is fairly straightforward. We make sure it's in the form ax squared plus bx plus c. We take x plus half of the coefficient on the x term with its sign. So we get x plus 2 and we square this. We subtract away this number squared, which is negative 4, and simply add the negative 5 back on. So we get x plus 2 all squared minus 9. Now this would be in the form of x plus p all squared minus q. And the reason I haven't put the p, q and r in the form we looked at before is that the value outside here was the coefficient on the x squared term, and it being 1, we don't need to really concern ourselves with this. Now, what's the use of this? Let's look at this graphically. If I drew a graph of this, we've got two transformations. This gives us a basic transformation of the following. It gives us negative 2, negative 9. So if we pick up the graph, this was the graph of x squared. If we take x squared, then what we know is it's a parabola like so, roughly like this. This has moved 2 to the left and 9 down. So what we've now got is this scenario going on right here. This is the completed square, and let's get rid of the old one. Right. Now what we can do from this is look at a couple of things. If we'd set this to 0 and solved it, then what we would have found are our points of intersection, which we'll look at later. But this has now created us, and hopefully that'll, it's not too fantastic, we've created an axis of symmetry. The axis of symmetry is around the point x is equal to negative 2. It's symmetric around this point, and that point right there at minus 2, comma minus 9 is the minimum point. The minimum point on the graph. So by completing the square, we've just shown two graph transformations. Okay, let's move on. What happens if now that it isn't an even number that we're dealing with? Let's look at this one. X squared plus 6x minus 1. Now, what we're going to do is take half of the coefficient from here. And again, this is a positive even number, so we're going to take x plus 3 and we're going to square that. We subtract away 9 and subtract away 1. So our completed square is x plus 3 all squared minus 10. So your minimum point on that graph is negative 3, negative 10. Just think of the basic transformations. X minus a, if you've got the f of x minus a, then what you've got is a translation of a units. Okay, let's do this one then. X squared plus 3x minus 1. So now we can do one with an odd number in terms of x. So we take x plus half the coefficient with its sign plus 3 over 2 all squared minus this number squared, which is minus 9 over 4. And then we got minus 1, which I'm going to write as minus 4 over 4. So we could write this one now as x plus 3 over 2 all squared minus 13 over 4. So again, our minimum point is minus 3 over 2 minus 13 over 4. I've done quite a lengthy tutorial on completing the square, and you can check that out. Now let's look at this one here. X squared minus 5x plus 2. We take half the coefficient in with its sign. So x minus 5 over 2 all squared minus 25 over 4 plus, and now if we switch this into 4s, we're going to have plus 8 over 4. So x minus 5 over 2 all squared minus 17 over 4. So your minimum point is the following. We're going to have a minimum point down here at positive 5 over 2, negative 17 over 4. So it's going to look like something like that. Okay, with this point here being 5 over 2, comma, negative 17 over 4. And your axis of symmetry is the line x equals 5 over 2. What happens, for example, if we have now, when it's a negative, let's do this one and make this negative x squared. Say we've got negative x squared plus 12x plus 3. What happens then? Well, we go back to our first original example when we had the number out front. What we do is we take outside the negative. We complete the square on a positive x squared coefficient. So we end up taking the negative out and we end up with this scenario. We just go ahead and complete the square inside these square brackets. So x, and take half the coefficient, so it's going to be x minus 6 all squared minus 36 minus 3. So I've taken half the coefficient, squared it out. What we now do is run the negative back through, so we get negative x minus 6 all squared minus 39 becomes plus 39. Okay, if we now look at what we've got another quadratic in completed square form, but we have a maximum point. So this point now is at 639, and this shows us that this is being reflected in the x-axis. So we end up with having a negative parabola like so. It looks something very, well, it may look slightly different, but it'll give you some idea. It just looks slightly different on the axis. If I'm being 100% picky, look more something like that. So this point at the top here is going to be the point 639, positive 39. And this right here is going to be a maximum. Okay, so your axis of symmetry here, but this is a maximum point. Okay. We can also use completing the square to solve, and I'll give you some examples of this. Let's just use this first one. This is quite a nice one to look at. X squared minus 4x plus 3 equals 0. We take half the coefficient with its sign, x minus 2 all squared. We subtract away that number squared, which is going to give us minus 4, and then we plus the 3, and that's equal to 0. So x minus 2 all squared minus, we got minus 1, is equal to 0. X minus 2 all squared is equal to 1. X minus 2 is equal to plus or minus the square root of 1. So x minus 2 is equal to plus or minus 1, and x is equal to 2, adding 2 to both sides, plus or minus 1. So x is equal to 1 on here. So what we're going to have, x is going to equal 1, or x is going to equal 3. Now, if you look back at the quadratic we just solved, let's factor it. X minus 1, x minus 3. X is equal to 1, and x is equal to 3. So you say, why didn't you factor that? You would do, but this shows that this works as a method. Take half the coefficient in, square it, subtract the constant from both sides, and then just square root. And the reason we use a completed square to solve is sometimes we simply can't factor them. So let's look at this one right now. Will this factor? The answer is no. X squared minus 6x minus 4. You've tried to factor it before. Two numbers that multiply to give 4 and add to give minus 6. That doesn't happen. X minus 3, take half the coefficient, square it. Subtract away this number squared, and then we got our minus 4. Some people like to take the constant straight over. I'm not bothered, you can do that if you want. This leaves us x minus 3 all squared equal to, adding the constants to the other side, 13. Square rooting both sides, x minus 3 is equal to plus or minus root 13, which is a third. So x is equal to 3 plus or minus the root of 13. Now what would this look like on a graph? Well, we know that we're going to have the following. We can start adding some information to this. We can see that it's going to have a minimum point now here at 3, negative 13. So down here is our minimum point. So 3, negative 13. And what we've got are some solutions at 3 plus root 13. Now, if we think about root 13, root 9 is 3, root 16 is 4. So we'll take a wild stab, but this is going to be about 3.5. So 3 plus 3.5 is going to give us about 6.5. But we can only say approximately 6.5. What we do is put the exact value. This is what we call the exact value, and you will leave it in that form. And then 3 minus about 3.5 is going to give us about, just here, at negative 0.5, give or take. And we would write this exact form as 3 minus root 13, 0. The parabola opens upwards, and we get this scenario going on. Now, out of interest, this point here, if x was 0, this point is going to be, and as you can probably appreciate, this is factually inaccurate, but that point should be negative, this point here should be negative 4. Okay, so that's 0, negative 4. Okay, you can probably see it's not 100% accurate. Now, if we look at this, and we use the quadratic equation to solve this, let's grab a calculator. So, minus b, which is going to be plus 6, plus or minus the square root of b squared, which is going to be 36, minus 4 lots of a, which is going to be 1, multiplied by c, which is negative 4, all over 2a, which is going to be 2. If we look at our solutions, 3 plus root 13, 3 minus root 13. So it's an alternative for the point here. So this is what it looked like, minimum point of 3, negative 13, because that is the completed square. If we'd simply completed the square, we would have had x minus 3 all squared minus 13, and that would have been our completed square, which gives us our minimum point and our axis of symmetry. Axis of symmetry is x is equal to 3. Minimum point 3, negative 13. We can see this point right here is when, if x is 0, we just get the constant and the negative 4, and then we got our two possible solutions. So completing the square gives us a lot of information. Okay, what we'll do now is complete the square when the coefficient is not 1. Now, this, in terms of what you do with this, if you're simply solving, then you can get rid of that value, and we'll look at that shortly. But what we need to do is ensure that when we're completing the square, the coefficient on the x squared is just 1. So let's divide that first one now by 2. So we take 2 outside, we get x squared plus 4x minus 1 half. So I've divided all of this by the value of 2. Okay. Again, some people like to take the constant the other side. I prefer to do my working in here, but it's entirely up to you. There are different ways to do this. So we've divided it all by 2. Let me take half the coefficient. So x plus half the coefficient all squared, minus 4, and minus 1 half. Now if we look at this and we run this back through, now all we've got to do is run the 2 back through. So it becomes 2, the quantity, x plus 2 all squared, minus 8, minus 1, which is going to give us minus 9. So the completed square, And this is the original form we visited, px plus q all squared minus r, or however they want to, or plus r on the end, however they want to put it. This is a completed square. In terms of a graphical representation, there are three transformations that have gone on. We've got now the horizontal. So if you look at these, and you don't have to do them in a certain, well, we'll ignore the order for now. What we're saying then is -2, so it's moved 2 to the left. It's had a scale factor stretch, positive to parallel to the positive y-axis of 2, and then we've had a translation of -9. In terms of your translations here, the order in which we do them we will discuss later, but essentially there are three transformations going on there from the original graph of y is equal to the x squared, or the f of x is x squared. Now that's a completed square. If you're using the completed square to simply solve this, and we've got a coefficient that is not 1, then we can start doing something slightly different. And we'll do it with this one. We're purely solving this time. So I've got 3x squared plus 12x minus 8. So we take the 3 outside the brackets, and all we're doing is finding points of intersection now. So x squared plus 4x minus 8 over 3. I've just divided all of these terms now by the 3. If we complete the square inside these brackets, we get x plus 2 all squared minus 4 minus 8 over 3. And that's equal to 0. At this stage we can simply divide both sides, so that can disappear. So all we've got to do is solve this. So what we've got is x plus 2 all squared, and taking the constants to the other side, I've got minus, so that's going to become 8 over 3. Now if I've got add in 12, I can call that plus 12 over 3. 12 over 3 is 4. So what we got is x plus 2 all squared, and then we're going to have that's equal to 20 over 3. Now at this stage we can square root both sides, okay? So we're taking the 3 out, and we're going to get now x plus 2 is going to equal plus or minus the root, and we can split this up. We can write this as the root of a complete root, or we can write it as root 20 over root 3. So now x is going to equal -2 plus or minus root 20 over 3, and I'm going to rationalise that to give us now root 60 over 3. And again, you can look at, if you want to tidy that root 60 up, you can certainly tidy that up. I've multiplied top and bottom by root 3. So if you think of 60, 60 divided by 2 will give you 30, divided by 2 will give you 15, and then it will come into 3 and 5. So we could write this as 2 root 15. So we could have x is equal to -2 plus or minus 2 root 15 over 3. You could even factor out the 2 if you really wanted. Now let's look at that one in a calculator and solve for it. So minus b is going to be -12 plus or minus the square root of 12 squared, which is 144, minus 4 lots of a, which is 3 this time, multiplied by the c, which is -8. And that's all going to be over 2a, which is going to give me 6. If you think this is the ax squared plus bx plus c, and I've just fed this straight through the quadratic equation which we looked at last time. Okay, and look at that, spot on. What have they got? Okay, well that makes sense, because what they've done, they've combined this -2, so they put it all over 3. So if you think if we put it all over 3, then we're going to get -6 plus it. I've just got the constant out there. They've put it as 1, or the calculators put it as 1. Exactly the same answer as we've got, which is good. So there we go. That is how to use the completed square. So this is purely, I've just solved. If you were asked to give the completed square, you would want to run the 3 back through this. So if you were asked just to give the completed square, what we would have here is 3, the quantity x plus 2, all squared, minus 12, and then minus 8. That looks right. So 3 x plus 2 all squared minus 20. That would be just the completed square, but because we were solving, we can get rid of that 3. And the reason that there's a difference is that it has a significantly different graphical representation than it did before. So there we go. There is completing the square, and it's the influence it has on graph transformations, and we've used it to solve purely based. Looked at it on working it out as the value in third form. This is third form. The one that we did earlier, where I did the graph. Whatever you do, don't put plus or minus about 6.5 or 6.5 and minus 0.5. We leave it in what we call exact form. Exact form asserts fractions, generally rational fractions, where you've rationalized the denominator, pi, e, log something. These are what we call exact fractions. So there we go. And hopefully there's been none of my notorious arithmetic errors in there. If there are, just drop me a line, but that should help you out on those. And also there is an additional video on completing the square, which I'll link to this one.